So we represent compounds with chemical formulas. The chemical formula tells us which elements are in the compound and how many atoms of each, or how many ions of each, are present. So we use the element symbols, and then we use a subscript following the symbol to tell how many there are. So water is represented as H2O. So H2, the 2 tells us there are 2 hydrogen atoms, and the O tells us there's 1 oxygen atom. We tend not to write the number 1, because if we had more than 1 oxygen, there would be a number, 2, 3, or 4, right? If there was no oxygen, we wouldn't write the symbol. So if there's 1, we just write the chemical symbol and leave it alone. Carbon tetrachloride is CCl4. You need to be a little careful here. Sometimes these things can be a little confusing, because you might see that as carbon-carbon and 4 iodines, right? If it was 2 carbons, it would be C2. We wouldn't have C and C next to each other. And so that's a clue that this is Cl and not carbon iodine. I always write my chlorines and all my lowercase l's as a script L to make sure that it doesn't look like carbon and iodide, carbon or iodine. Yes?
Is this still chapter 2?
Nope, this is chapter 3. So there are different types of chemical formulas. Empirical, molecular, and structural formulas. Empirical is a word that means from experiment or from experience. So an empirical formula tells us the relative number of atoms of each element in a compound. It doesn't tell us the number in a molecule, it tells us the lowest ratio. And it comes from experiment, and we're going to actually do an experiment where we determine the empirical formula of a compound. So let's look at hydrogen peroxide. The formula for hydrogen peroxide is H2O2. In a molecule, there are 2 hydrogens and 2 oxygens. That is not the empirical formula, though. The empirical formula is the lowest ratio. So it's 2 to 2, 2 hydrogens to 2 oxygens. The lowest ratio is 1 to 1. So that's what an empirical formula gives us. This is the empirical formula. This is the actual molecular formula. So it's just the lowest ratio. Molecular formula is more useful. It gives us the actual number of atoms in a molecule. So for this compound, C4H8, that is describing the actual molecule, 4 carbon atoms, 8 hydrogen atoms. We should be able to look at that and tell what the empirical formula is, the lowest ratio. So we look at the subscripts, 4 to 8, and you can think of that as a fraction or a ratio. How would you simplify that? Well, both of those numbers can be divided by 4. So the empirical formula is CH2. It's a ratio of 1 carbon to 2 hydrogens. For B2H6, these subscripts 2 and 6 have a common factor. The largest common factor is 2, and so we can divide both of them by 2, and we get the lowest ratio of 1 to 3, BH3. For some compounds, the molecular formula and the empirical formula are the same. We looked at carbon tetrachloride, CCl4. That's a ratio of 1 to 4. We can't simplify that any further. And so the empirical formula and the molecular formula for that compound are exactly the same. Structural formulas are also used. Here we're showing how the atoms in a molecule are connected to each other. And we use lines to represent the covalent bonds where the electrons are being shared. We use a single line for a single bond, a double line for a double bond, and a triple line for a triple bond. So if there's 3 lines, that means it's a triple bond. Which formula we use depends on how much we know about the compound and what we're trying to communicate to others. The structural formula gives us the most information, but it's sometimes really awkward to write, and especially to put into a computer. You have to get out a graphics program of some kind. It's a pain in the neck. But it gives a lot of information. Empirical formula communicates the least, but it's much easier to type into a computer. So which one we use just depends on the situation, and you would not be expected to know that. What you need to know is you need to be able to understand what all of them mean, the empirical, molecular, and structural. So one of the things we need to be able to do is write empirical formulas from their molecular formulas. So for the compound C5H12, that's the molecular formula. What's the empirical formula? It's the same because a ratio of 5 to 12 cannot be simplified. 5 and 12, their only common factor is 1, and that doesn't change anything. What about Hg2Cl2? HgCl, because both 2 and 2 are divisible by 2. So we could simplify that. It's a 1-to-1 ratio. How about C2H4O2? CH2O. We take all the subscripts, 2, 4, and 2, divide all of them by 2. That maintains the same ratio, but puts it in the lowest form. Any questions? We also use models, and molecular models are more accurate even than formulas because they give us a picture of the actual shape of the molecule. Ball and stick models are common. Here we use balls to represent the atoms, and the chemical bonds are represented as sticks. And you may have seen model kits like this before, these little gray boxes over here. These are examples of ball and stick models. They're kind of like scientific tinker toys. They're kind of fun, actually. We tend to use a color code to represent specific elements. That's not necessarily universally used, but this is the colors that those model kits use and the ones that the textbook uses. So when you see the different colored balls in the models, like the water is red and white, it's because we've decided to use white for hydrogen and red for oxygen. So this slide shows us 4 different ways to represent the same molecule. So the molecular formula is CH4. That just tells us how many carbons, how many hydrogens are in one molecule. The structural formula shows that the hydrogens are all bonded to the carbon with single bonds. There are other ways that you could combine those different atoms, but this is how they are combined in this molecule. You can make the ball and stick model. Yeah.
For the ball and stick model, how would you actually do a triple bond?
How would you do a triple bond? That's a good question. So in the ball and stick model, there are some short sticks and there are some longer sticks that are flexible. And you can actually connect 3 of those long flexible sticks between the same 2 balls. Yeah. So ball and stick model is going to look like this. And this now is starting to tell us about the shape of the molecule. This is not flat as this appears. Yes?
Are we going to use Lewis dot?
We are going to use Lewis dot structures. Not yet. And then probably the most accurate model is what's called the space-filling model. So it is very convenient to think of molecules like this. And I tend to think of them that way because it's easy to visualize. But do they actually look like that? No, they don't. When a hydrogen and a carbon atom are sharing an electron, they kind of smush together, right? And so a space-filling model allows us to see that it's really kind of more of a lumpy sphere than this, this thing looks like you could use it as a massage tool or something. It does work, actually. We've tried it. So this table from your book is just, to give you an idea of what these different things would look like. So we have several different compounds here. Their names, the empirical formula, the molecular formula, the structural formula. Now, glucose, C6H12O6. There's lots of ways you could put those things together. You wouldn't necessarily come up with that. And the very interesting thing about glucose, it's what's called a hexose because it has 6 carbons. There are a large number of hexose sugars, and the differences between them are incredibly subtle. Differences in where this double bonded oxygen is and how these are arranged around these individual carbons. And those are differences that are recognized by your body. Your body metabolizes glucose very nicely. That's the sugar that gets into your blood and feeds your brain. There are other sugars, though, that your body can't do anything with. Got the same molecular formula, but your body says, can't do anything with this one. So here's the structural formula and ball and stick model. This is starting to look like some sort of a sculpture. Yes?
So basically, if the structural formula isn't the right one, your body can't use it?
Yeah. Yeah, biochemistry is a very interesting branch of chemistry. Your body has enzymes that promote reactions of certain compounds, and if it's the wrong sugar, like if this oxygen and this hydrogen switch places, it's going to be a different sugar, and your body will recognize that because the enzyme won't fit right, and so it won't react. Yeah. This is the space filling model, which is more the shape of the glucose molecule. But you can tell how it would be hard to look at that, especially a two-dimensional picture of it, because you can't see what's on the other side. The ball and stick model is open, and so we can see what's on the other side and see what everything is. Here we've got the blue, sorry, get down here, the blue one is the nitrogen. Any questions?